Hello, everyone. Maps. I'm Paul Dorman. I'm here with my second vector tile talk of the day. This is also about OpenStreetMap's new vector tiles, but this is a technical talk into some of the details of how they are served. I've been working for the OpenStreetMap Foundation as a part-time contractor. I'm also heavily involved with a lot of OpenStreetMap stuff on the operations working group. I've been around OSM since 2010 or so. I had a talk earlier today about how to use the tiles, so that's if you want to display a map on your website, that kind of stuff. This is if you want to serve your own tiles, or you are serving your own tiles, and some of the tricks that are necessary to serve planet-wide tiles with minutely updates. There was also before this another talk about generating your own tiles, which with Plain Tiler, and that one was differed because that was dealing with generating all at once, not minutely, just so that you know what all of these different talks going on about vector tiles are covering. To discuss what's going on, though, we need to know what tiles are. Tiles took off mid-2000s as a way to have a zoomable and panable map. They exist because they are much more cacheable than existing technologies like WMS, and these days almost all interactive maps that you use are going to be using tiles. The important thing about tiles is there are a lot of them. So for raster tiles, about 360 billion. Most of them are ocean tiles and are very tiny, but the ones that people view are more complicated because that's where stuff is. And for the vector tiles, they're shortbread tiles, so there are about 360 million tiles that a user could potentially request. Again, most of them are water, so they won't. But what makes up these tiles? So raster tiles are images, which I'm sure everyone has seen images before, but it's a 2D array of colors. Vector tiles are different because they don't have colors or anything like that. They have layers with geometries. There's different formats out there, but the one that we're serving, and the most common one right now, is Mapbox vector tiles. They've got a lot of properties, but there's a few key ones for the serving of them. The vector tiles are formed by concatenation of multiple layers together. And layers with no contents are 0 bytes. Both of those properties are extremely important later on. If you're actually writing the code to generate them, the geometry stuff is much more interesting, but for the serving part, it's properties like these that matter. Before I get right into the vector tile infrastructure, though, just for comparison, I want to go over the raster tile. Because there are so many raster tiles, we combine them into 8x8 meta tiles. And because there are so many, at high zooms, they only get re-rendered at time of user request. The work does not get done in advance. This leads to some problems. The load scales with demand and frequency of updates. The more users hitting the map, the more it's going to have to render, but also the more updates, the more frequent those users are going to need to have a new tile rendered in the first place. The tiles are stored, but the hit ratio is fairly poor because there are so many tiles. And although it's not inherent to raster tiles, the particular system that we use has a queue system that is very complicated, and I'm not going to go over. I did a community post that simplifies it, but it's still quite complicated. So what do we do with vector tiles instead? So a high-level overview, just so that you know where we are later in the talk, is we use software called OSM2PG to take OpenStreetMap data and changes to OpenStreetMap data, and it puts it in PostGIS tables. There are some Lua scripts that tell it how to do this. So they say this feature goes into the buildings table, this feature goes into the roads table, stuff like that. There's a program called OSM2PG SQL Replicate that fetches the changes and tells OSM2PG SQL to run, and then takes the list of, it knows what tiles need to have been updated. And then the software tile kiln is used to run some PostGIS queries to generate tiles and save the results in storage. Tile kiln is also used to fetch tiles from storage and serve them over HTTP for requests. And those processes are separate ones. Just pulling up I have some additional notes here, sorry. So the first part about generating vector tiles is generation. This involves a bunch of complicated geometry that you really don't want to write code to do it, because everyone who I've seen write code and release it gets it wrong the first time around. Instead, we're using PostGIS. PostGIS has functions in it that will deal with the complicated analytical geometry that needs to be done. And the reason why this is so important is that invalid geometries are very bad. It's not just the feature that has invalid geometry that gets screwed up. It can screw up the display of the entire tile and mean that it's blank or various other problems. So in PostGIS, it's st as mvt geom and st as mvt that handle all of it. Mvt geom does manipulation. The other one writes to the appropriate format. PostGIS also allows you, with this setup, to curate just one tile. Software like Plaintiler in the previous workshop is great if you want to curate all the tiles for the planet in 2 hours. It will also curate one tile in 2 hours. So it's designed for a very different work case than minutely updates, where you need to generate tiles every 60 seconds, but not that many. PostGIS also gives some good advantages for advanced geometry processing. Once the tiles are generated, they need to be stored. There is no good solution here. There are 360 million tiles, most of which are 100 bytes or so, but there are outliers that can be a couple of megs. I'm not going to go through all the potential options, but we're storing them in Postgres without using PostGIS. It's just a table filled with zoom, x and y, and the tile contents. This has got some operational advantages because we already need Postgres for the geometry part, so we're not running yet another piece of software. And in the OSMF, we know how to run Postgres databases since we've got a number of them. It's also only got about 50 bytes per tile overhead, which is comparatively pretty good. So this is generation storage, and this leads to the original plan. The original plan is to generate all 360 million tiles, and then serving them as a completely separate process that is a very simple query. This means that the load essentially is the same no matter how many users are hitting it, because all the load is done with the pre-generation and the updates. It means that if the generation or updates fail, you don't get broken tiles, you get old tiles, which is not ideal, but it's okay. It works very well, kind of. It's slow. It can't. I have done it before, and it can be done, but it means that you have to be very careful, and stuff like updating the tile schema and stuff like that means you have to regenerate all of the tiles. It also works, there's a similar problem for coastlines because the coastlines change every day and you don't want to regenerate all the tiles every day. But I had a fallback plan from the start, which was live mode. This is a different mode of tile kiln. It serves some storage when available. And if it's not available, it will make it and then store it. This allows the option of deleting tiles and re-rendering on demand. This is quite useful. For example, if there's vandalism, severe vandalism, and we need to go in, we can just delete the tiles and get rid of them, and then they will repopulate as their requests. But coastlines are still awkward. This will come up a few more times. Coastlines are different. But this was still running a bit slow. So, layers. This is where what layers are matter. Most features in OSM are going to go into 0 to 2 layers. A building's going to only go into the building layer. A road's going to go into maybe a road and a road names layer. Generally, a feature just ends up 1 or 2 places. So what this means is that when you say add a new building as an edit, only the building layer actually is changed. The other ones remain the same. The ocean layer the ocean is its own layer, so it's particularly important here because it only changes with the daily coastline updates. Rebuilding a full tile, like rebuilding all the layers for a tile, when any one thing changes, wastes a lot of work. That means it's slower. Another factor is that the complex layers, like land use and oceans, the stuff that takes more time to generate, tend to actually not be edited as frequently, whereas quick stuff, buildings, they tend to be edited more often. So the solution is store by layer. This is not a new idea. Mapbox did this, has been doing this for over a decade. Still a decently big refactor, but fundamentally it's taking advantage of those properties of MVTs before, that you form them by concatenating layers together. So to do this, all of the layers get stored into a tile, for each tile into one row. If the layer is not yet generated, it's null. So now to serve, you fetch all the layers, join them together. If you're serving in live mode, you fetch all the layers, you see which ones are missing, and then you only generate the missing ones. This really helps. And where it really helps is updates. Updates now, instead of the traditional way to do updates is you have a list of changed tiles and you feed that in through OSMF SQL expire outputs and such. Now it's taking tile layer pairs, so this layer on this tile has changed. No existing tools provide that, but you can generate them reasonably easily with a bit of manipulation. The storage side is simple. You're just concatenating a bunch of fields together that because there's no headers or footers to the format really, it's just an SQL concatenate statement. It does involve a lot of programmatically generated SQL because there are a lot of layer names and you have to build the SQL in code, but running it is simple. So to understand how updates work, I'm going to go back to OSMF SQL. So in OSMF SQL, you have a flex script, which is what defines what goes where. It will also allow you to define expire outputs, which will write a list of changed tiles to a file. And what you can do is you can have one expire output for each different table. This means that this table you can now say this layer has changed in this tiles. And then if you do a bit of string manipulation, you can get that into the format tile kiln once. And it will then do that to get knowledge of which table you use that knowledge with knowledge of what you've written to get a list of all the tiles that have changed, and for each of those tiles, which layers. So then you can go through and do that. And this is surprisingly fast. It was probably at least 50 times faster. I don't have solid numbers on that, but it's definitely over 10 times. But oceans are still a problem. Oceans are a problem because of how they're represented in OSM. It's natural equals coastline, which only makes sense if you look at the coastlines for the entire world at once. There's a process that runs every day. Johan runs it, I think, back there, and it generates shape files which have polygons for the ocean. The problem is that there's no diffs. There is information on what's changed, but if you ever miss a day, then you've lost that information. So what we do is the loading script has both the old data from the previous day that it's been using and the new data in the database at the same time. And you can do various geometry tricks, and you can get a list of changed tiles. Then you can, for those tiles, regenerate the oceans. That means that you're not regenerating 360 million ocean tiles when typically only about 1,000 of them have changed a day. This was the last piece needed, and it means that now we are doing minutely updates, and I don't have exact numbers, but most of the time it's done in far less than a minute. Typical is about 10 seconds, which is about as low as you can reasonably get given costs for starting and stopping processes. And that's the bulk of how we manage to generate minutely vector tiles. Going by layers was really the key. And there are some other interesting points, which, since I have time, I will just go over. Tiles are really all about caching. That's why we use them. And caching, one way to do caching is with e-tags. It lets you see if e-tags in general let you see if a file that you have in your cache is identical to the one that the server has. The problem is that for various reasons, the two tiles with the same contents may not be byte for byte identical. That means they have different e-tags. So if you have one tile that's on two different backends with different binary representation and different e-tags, it will tend to, if you get a flip between one and the other, and ruin your caching. Weak e-tags work for this, but they're difficult to do here. So instead, you could actually just get rid of e-tags and use last modified, which is an older way of doing caching, but it still works. And it means that it will settle on one representation or the other, whichever has the more recent timestamp. And it doesn't really matter which, because their contents are the same. It's just they're not byte for byte the same. The other thing is that is interesting is multiple tile sets. We will, in the future, want to be able to serve more than one set of tiles out of tile kiln. This is for a couple of reasons. One is that when Shortbread 2.0 comes out, we don't want to just cut off the Shortbread 1.0 tiles and have everyone break until they've moved to the 2.0 tiles. We need some period where we have both of them. There is also work being planned that will involve different schema work. There's no ETA on this. It's not technically hard, it's just you really at this point are passing around so many configuration options. it needs to be, you need to start looking at different formats for doing that than putting them on the command line. Because each tile set, you need to specify a couple of databases, where the config file is, stuff like that. I think that, yeah, that wraps up what I've got today. I've left time for questions since knowing people here, I'm anticipating some good questions, so I'll open it up for questions. Yep.
Simple question. So is that one database per layer or one table per layer, and how big does it end up being?
So you've got one database that stores the geospatial data and another that stores the tiles. The database with the geospatial layer has multiple tables, which they're not one-to-one with the layers, but they're sort of close. But you can go from you know that if this table has changed, these layers have changed, where it's one or two layers. In the storage size, it's one partitioned table per tile set, and it's multiple columns so you've got one column with each layer, as well as one column with the last modified date of each layer. The reason for doing that instead of having one row per tile layer is twofold. One is that 50 byte per tile overhead suddenly becomes 50 bytes per tile layer, which means it's 26 times larger, and that is a problem. The other problem is that it's more difficult to have a solid idea of a null layer if you're doing it as one row, one layer. And it's important that you don't lose track of those, because those are the ones that you need to generate at request time.
Your cache and E-tag issue, and so the lack of a stable binary representation there. What do you think sort of causes that? Is that floating point in the files, or is it timestamps?
Ultimately, so this is a familiar issue from raster tiles, where if you have two meta tile edges and there is a point that appears in both tiles, if it can appear incorrectly if it appears at a different order in the query results. So you order the stuff that you care about, but for stuff like, say, water polygons, it doesn't matter what order they are in the tile. They're all just going to be done with a fill. But depending on when the database was loaded, what reindexing has been done, how the vacuum has run, there is no 100% guarantee that the stuff will come out in the same order unless you explicitly order by it, which isn't necessary. So that's why, at least for the scenarios I've seen, that's why they aren't binary identical. There might be other non-deterministic parts going on.
I'll ask a question.
Sure.
Where can we actually see these vector tiles being used?
You could see them in my presentation earlier today.
Can we actually see a minutely update happen?
Maybe.
So show us the layer first, Paul. So it's the shortbread layer on OpenStreetMap.org where you can see these tiles.
Yeah.
And Paul's created a whole lot of magic that does all these minutely updates.
So I could show you a tile update. The problem is that it's just going to be all in text representation and not not very informative.
Just renamed on D to something else.
Just go to the US. Just go to the US. There's plenty of towns that are not mapped. Add one little building. You find it easy.
Yeah.
We've only got 3 minutes. We've only got 3 minutes. So.
I say minutely, but there is some caching involved as well, which means that it can take more than 60 seconds to go end to end. Yeah.
Quick question, around documentation, is tile kill got documentation around it so that somebody can take it and say, yeah, I'll set this up, I've already got some vector tiles on the website, could I apply that process to my style and sort of set up a database? Effectively replacing like a tile maker, which is just like a one-shot documentation file.
So tile kiln occupy is a similar place to something like Martin or plain tiler, in that you have to give it a configuration for how are you going to generate the tiles. And because the methods are so different, you can't directly port your tile maker config. If you do the different config, then both options will end up serving tiles in the familiar ZXY over HTTP. And if you've built the configs to put the same contents in the same way, you can swap them. In fact, with the shortbread tiles, it's a good example of this. You can use OSMF ones. You could use GeoFabric's TileMaker ones. You could use BB Bike has some. Plain Tiler has a config, and all of these, when served over HTTPS, are interchangeable.
The question is more around the military updates that tile kiln runs. Is the set of information you need to actually settle that one nicely documented so that somebody can follow it, or is it some pull requests accepted?
So the problem there is that the tile kiln part is well documented. It's piecing together, it's putting together the glue to get updates from OSM to PG-SQL into tile kiln, which, I mean, it's in Chef, it is open source, but it is poorly documented how that happens.
There's not an equivalent of like the OSM2 PGSQL documentation on how the expiry works and what parameters it takes and all that kind of stuff.
You have to use that. You have to use that OSM to PG-SQL documentation and the tile kiln documentation and put them together. It is something that can be improved. Yeah. It is also fairly familiar to anyone who's done minutely tiles before. It's very much based on the existing process. I see some heads nodding who have probably used the render mod tile thing.
Yeah, is mod tile as Apache still part of the stable?
No, there is actually there's no mod tile, there's no mapnik, and as it happens, there's no Apache. We use Nginx to terminate the HTTPS connections. We could have used Apache, but the technology that it shares in common with that is around OSM to PG-SQL, and that's it.
I think we're kind of out of time. So,
Thank you.